question was, why would you want to have a transformer? What's the purpose? It's all well and good to say that we could do this, but why would you want to do this, right? So this has to do with electrical power transmission. What we do is we step up the voltage at the power plant for transmission along high voltage lines, and then we step it down in our cities, and then we step it down again at our house level. Okay, that's what we do. The why, let's get to it. Okay, so the transmission of electrical power. Transmission of electrical power makes use of transformers at various stages between the power plant and our houses. And to talk about why that's useful, we got to throw some equations at you, okay? Because it's really the language that we have to speak here. One equation that we know from years ago is V is equal to IR. Remember that one? Ohm's law? Yeah, that's an oldie but a goodie. And so I is equal to V over R is another way to rearrange Ohm's law. So I want to put a box around that variant and just call that Ohm's law for a second. I'm not going to call it like equation 1 prime or something like that. We got Ohm's law, and then we also said that power is equal to V times I. That was something that we said just today. But if you sub this I into power is equal to VI, can you see that you could come up with the equation power is equal to V squared over R? If I sub this equation into this equation. I'm just pointing at it with my fingers because I don't want to make this a big long, derivation or something like that, okay? So sub this into this, you get this. I'll put a box around that because that's valuable. I'll put a box around this because it's valuable. But then I could also sub this, the original Ohm's law, into this. And if I do that, I end up getting power is equal to, well, what do I get? Look, V into the V spot. Can you see that it's I squared R? Because it would be I squared I, R. So I squared R. Of course, we know that power is also equal to delta E over delta T, but that's not really using these equations. It's just leaning back on the definition. Now, why would we want to have these equations? Well, honestly, this one's nice because I can measure voltage with a voltmeter and current with an ammeter. But maybe I know the resistance of a circuit too, and so I could calculate power that way. But if we said earlier that with these transformers, due to conservation of energy, power in the primary is equal to primary in the secondary, right? So they both have the same power. They're both delivering the same amount of energy per second, because that's what the definition of power is, amount of energy delivered per second. So the primary coil gets delivered the same amount of joules per second as the secondary one. We're just transferring power from one to the next, right? Nice smooth transfer of power. Yeah?
So in Ohm's law, what does R stand for?
R stands for the resistance of the circuit in Ohm's law. Yeah, measured in ohms. Yeah. But when I talk about this primary and secondary, there's the same amount of power in both. What I can say is that high power or high voltage for a constant power, like if I keep power as a control, as a constant, high voltage for a constant power results in what? High or low current? Isn't it low? If I keep the power constant and I jack up the voltage, that's going to jack down the current, right? So low, I'll put it in capital letters to draw attention, current. This is just me thinking cause and effect, okay? The next arrow in this cause and effect logic sequence is low current results in less energy loss per second. And people say, well, why does low current produce less energy loss in per second? Well, this is an issue of why electrical energy or how electrical energy gets dissipated. The reason is due to electrical resistance. Electrical resistance really is thermal energy loss as electrons zip from one atom to the next atom. So if they have to zip from between atoms, less atoms per second, that means that less thermal heating is going to happen per second. Okay? So less atomic leaps per second. Obviously, this is not formal language. Means less energy loss per second. I'll just say per s for second. We'll say sec. So we don't think it's like PERS, okay? Then we could say, less energy loss per second equals higher efficiency. This is just logicking it out, right? And I don't want to be too granular about this logic, but doesn't higher efficiency and therefore less energy loss mean less energy cost? Because we're wasting less, right? So higher efficiency leads to cheaper energy. And really, I just kind of truncated the logic there because I ran out of paper. Because we could be more granular about why it's cheaper to lose less energy, but of course, life is cheaper if you drop less money out of your pockets. That's what it is. Like if we have more resistance and it's less efficient, we're just dropping money on the floor. We're dropping energy on the floor, right? And so we want life to be as efficient as possible with the power grid that we have, and the power production facilities that we have. So let's just say that this is the logical sequence for why we use high voltage power transmission lines. And we got them strung up. Hey, here in Canada, we got to ship our electricity all over this enormous space. Americans got the same problem, right? And we have an interconnected electrical system. Maybe a smaller system might not care as much, but we really, really care about high voltage transmission lines because we don't want to bleed money. And people say, well, why don't we just keep the voltage really, really high, right up into our houses? Anybody got an idea for why we don't have 240,000 volts in your wall socket? Any hypotheses? Yes. Yeah, that's true. The first child that licks a light bulb is gonna be a former child, right? Like this is gonna crispy critters with the pets. Like this is not a good idea. Anyway, so it really is for safety issues, efficiency for large distances. And you notice even at those large distances, I mentioned earlier about foolish people who try to steal copper from transformer stations. We have to protect the idiots with barbed wire. We have to protect the idiots by putting the electrical wires 100 feet up in the air, right? Don't climb an electrical tower just for fun. Don't scale the barbed wire fence that says don't scale me, right? This is all to protect you. The reason that we have the high voltage is just to save money. It makes sense. Okay?